So good morning, everyone. So my name is Itsaka Rakoto Nirena, and I'm a PhD student at INRIA Nancy in France. And this is a joint work with my supervisors, Steve Kramer, which is not here, and Vincent Cheval, who you can find in the audience. So maybe to begin with, slowly, here is just a list of names. So I guess that at least TLS and WPA2 ring a bell to you. And these are actually security protocols. So that is, they are distributed programs describing how agents can exchange some private data. So of course, the goal is to do that so with crypto and to ensure that no sensible information is leaked to unauthorized parties. But it's not as simple as that in practice because, as you can see, there are a lot of attacks that are found quite often, and you have somehow a security problem about these protocols. But the attacks that I mentioned here, they are not just random exploits you can find in the literature. They actually share one common property. And this property is essentially that these attacks do not even try to break the crypto protecting the communications. They just exploit the flow structures of the protocols. So somehow you can describe these attacks in a setting where the evil guy trying to break into your privacy can essentially read and write on communication channels, maybe perform denials of service, and that's all. So of course the attacker has access to some cryptographic functions, but they just use it as black boxes. So they do not try to break it or use side channels or anything. And this corresponds to what we call Dolev-Yao models. So the attacker has complete control over communication channels, but cryptography is just assumed ideal. So long story short, we just want to study like the logical structure of security protocols and to see whether we can detect some attack automatically. Well, but so far I've not made it so clear what we call a flow, or alternatively, what kind of security properties we want to prevent the attacker from violating. And there are two kinds of security properties, actually. So the first one is to state insecurity as the reachability of a bad event in the program, in the protocol. So for example, like a bad event could be the attacker can deduce my private key, for example. And one other possible way of formalizing insecurity is to state that the attacker has the ability to distinguish between two situations. So for example, I would say that the attacker breaks my anonymity when the attacker is able to distinguish between the situation where I am doing something and the situation where someone else is doing the same thing. And you can actually model a bunch of privacy type properties using these equivalences. So in the literature, you have some major automated tools for reachability properties. Quite a few complexity results enhancing our theoretical understanding of the problem. But for equivalence properties, it's less clear somehow. So just to focus on this second problem. But still, we're not the first ones on this track, and there are already some tools, automated analyzers for this problem. But since the theoretical problem is undecidable, of course, these tools have some limitation. And the first one is about the number of protocol sessions you consider in your attack scenarios. So either you can bound it, and so you only consider like a fixed number of protocol communications. Well, the attacker interference is still unbounded, but the number of messages sent by the protocol is bounded, or you can just consider the unbounded case. So like the practical interest of the bounded case is actually that we noticed that in practice, the number of protocol sessions you need to mount practical attacks are quite slow. So even if you bound the number of protocol sessions, you can find a lot of practical attacks in practice. One other possible limitation is sometimes tools can have false positives, so they detect attacks that are actually not mountable, or also the problem of handling the crypto underlying the protocol. So here crypto is ideal, so crypto is just a set of equations. but it's still a complicated part of the analysis. So, okay, this is the landscape where we set sail, and our contribution here is to provide an analyzer that lists a lot of these limitations. So an exact and terminating procedure for a large class of cryptographic primitives, and the only restriction we keep is on the bound for the number of honest agents, so a bound on the number of protocol sessions. And beside that, we also have a running implementation that is publicly available that I will present later, and a theoretical result to back up our experiments and show that our solution of the problem is optimal to some sense. Okay, so now I'm just going to give you a rough overview of how the tool works. So just to give you, to explain you what kind of decision procedure we have, and then I will jump to experimental section. So as I said, in the Dolevio model, everything is about the logical interaction between the attacker that controls the network and your honest agents in the protocol. So on the one hand, the attacker gets knowledge by spying on public outputs, on communication channels. And on the other hand, the attacker, whenever the protocol expects a message, the attacker can just craft something on its own and just send it to the protocol. And this is the source of infiniteness in the problem. So you have to quantify over all possible messages the attacker may want to craft, and this is why the problem is non-trivial, even when you bound the number of communication of the protocol. So you have to make some abstraction to get around this issue. And typically, a common technique is to rely on symbolic calculi. So here, instead of just considering the infinite number of all inputs, you just represent them as one symbolic variable. And these symbolic variables are extended with what we call symbolic constraints. So to fill the gap between the symbolic word and the concrete word. These symbolic constraints are of two kinds, and intuitively, so deducibility constraints and equations. So intuitively, deducibility constraints state that the attacker is able to craft some term. So for example, if you're considering an attack scenario where the attacker is crafting a term X and sends it to the protocol, the analyzer will just record a deducibility constraint on this crafted term. And equations, they are stating the relations between the messages exchanged by the protocol. So for example, if some message, some ciphertext is decrypted using some symmetric cryptography, then the analyzer will record an equation stating that the decryption key is the same as the encryption key. Well, I'm not going to give much details on how we then solve this constraint solving problem, which is at the core of our decision procedure, because it's a bit technical. But let me at least give you the name of the ingredients we use to do that. So the most important thing is our notion of most general solution. So we have a symbolic trace, which represents somehow one possible interleaving of the protocol. And we define a notion of most general solution of this trace. So this is a finite set of solutions that we can compute, and that characterizes the whole set of possible instances of this symbolic trace. So computing this set of most general solution is one of our most important contribution in there. And once you have that, we define something that we call a partition tree. So you have your two processes that whose equivalence is to be checked, so A and B. And what you do is that you just compare all pairs of symbolic execution, and you record that in a kind of tree, so what we call the partition tree. And then when you have built this very expensive tree, the equivalence problem can be rephrased as a syntactic reachability problem like in this tree. So yeah, let's say we don't care much about theory. And that, okay, we have a solution. There are lots of complicated proof, and let's just see what we get from that. So experiments. So here are a small sample of security protocols with some security properties. So for example, strong secrecy or vote privacy, because Helios is an electronic voting protocol. And I just put how much time DeepSec takes to perform the analysis, and as a baseline for comparison, I just put 2 other tools. And as you can see, when some other tools either have a too restricted scope, such as SATECIV here, or fail to complete the analysis due to a too costly procedure, DeepSec is essentially able to complete the analysis quite quickly. So this is a way for us to back up our claim that DeepSec raises the scope of the attacks that can be found in practice. So like these blue lightnings means that DeepSec was allowed to find an attack and to describe how the attack could be mounted in practice. Yeah, okay, so far so good, but this is not the end of the story, because as you can see, for example, in the last line, even with a small number of agents, like 11 agents, DeepSec takes like more than 2 hours to complete the analysis. So we could wonder, like, isn't there a way to be more efficient than that? Like, couldn't be like just find an exponentially better algorithm that could make analysis even better? And to answer this question, we resort to theoretical complexity tools. So here are 2 complexity results about the decision of equivalence that you can find in the literature. And essentially, so you have the passive attacker setting, where the attacker is only allowed to spy on public channels, but not to write on them. And the problem was proved p-time, provided that you fix your cryptographic primitives. And in the active setting, modulo some hypotheses that are verified in some examples, but clearly not all of them, then the problem becomes co-MP. And what we prove in our paper is that actually you have a big blow-up in both settings when you jump to the most general case. So in particular, you have like this co-NX lower bound, which is actually the complexity of the theoretical algorithm underlying DeepSec, which shows you that there is, well, intuitively no way in full generality to do much better than DeepSec does. And that the problem is actually very hard. So that's why we have sometimes these 2 hours running time for performing experiments. But still, I mean, when you say that the problem is co-NX complete, it's just like a theoretical bound relying on a very degenerated example. And you could wonder maybe in practice, you could get some better results. And that's what we think. So here are 2 examples of security properties that can be modeled by equivalence statements. So for example, you have vote privacy. So usually you state it as the equivalence of 2 situations where some votes have been swapped. And what you can notice is that these protocols, these 2 processes whose equivalence is to be checked, they really have a similar structure. Like you have the same number of agents, they have very similar rules, only some values are changed at some point. So maybe, I mean, that's current work, so that's not in the paper, but that's what we are doing now. We think that we can borrow just some techniques from, for example, model checking, and use some techniques called, for example, partial order reductions or symmetry analysis, just to speed up the analysis in practice. So right now we are just developing one of these techniques, and we think that this can both speed up the analysis, but also I think we can get theoretical complexity results to show that actually the speed up is substantial. Okay, so I'll just make a quick sum up of our contributions. Our goal was to study the logical flows of security protocols in a setting where you're bound the number of protocol sessions. And our tool, DeepSec, has the main characteristics that it was actually exact, so no approximation, no false positives. It was optimal to some theoretical sense, although we think that for practical protocol verification, there's still room for improvement, and that's what we're doing now. And there is a running implementation publicly available that you can check and try if you want. And I'm done. Thank you for your attention.
Questions? Me again? You make me so sad. Well, actually, so
Of the tools that you compare with, because you're symbolic, are any of the tools not symbolic and they can do things that you can't?
This is all right?
So you're doing a symbolic analysis.
Yeah.
But some of the tools, were any of them not symbolic and can catch things that you can't?
I mean, you're talking about the two tools like we compared against, right? Yeah, well, they are both working in the same setting as us. So it's just like somehow the details of how we perform the constraint solving that makes a difference between their solution and ours.
I see. Some of this smells like information flow, kind of talking about traces. Like,
Yeah.
are any tools like the hyper LTL or things like that? Like,
We have not studied such things, but yeah, maybe. I mean, there is a common keyword, but I don't know if there is a formal relation between those things. I mean, we have not investigated in this track, so maybe we can, but we have not yet.
okay. Other questions? They ran out of food, so
Well, it's lunchtime anyway. So.
go eat. Thank you all. Let's thank all the speakers again.